Hello, today we are going to discuss about diastereoselectivity in Aldol condensation reaction by means of Zimmerman-Traxler model. We know that Aldol condensation reaction is well-known reaction in organic chemistry. So the main thing is that in order to have aldol condensation, we want a carbonyl compound having alpha hydrogen. Okay. Along with a good base, we can have aldol condensation reaction. Here we can have a general carbonyl compound. LDA is a non-nucleophilic base, that is diisopropyl lithium diisopropylamide, another equivalent of carbonyl compound. We can see the general mechanism. The first step is that formation of E-enolate. So what will happen? LDA comes to the picture. It will abstract this alpha hydrogen, acidic hydrogen. So attack, shift. So you will end up with a very important reactive species in organic chemistry is called E-enolate. This is E-enolate. Why? Because it is E-enolate in all. Okay, that's why it is called E-enolate ion. Okay, it is very reactive species in organic chemistry. So this E-enolate can be either E-enolate or Z-enolate. So the direction of oxygen and this R2 in the same side, it is called Z-enolate. If it is in opposite, it is called E-enolate. Okay. Next step, nucleophilic attack of enolate to the next equivalent of carbonyl compound. We know that enolate is well known nucleophile. Okay. So shift, attack, shift. Okay. So you will end up with this species. On protonation, you will end up with the so-called aldol. So here we represented the stereochemistry, that is the unknown stereochemistry. We represented in wiggly arrow. So that means it can be either in wedge or dash. This OH in wedge or dash. That is the charm of this treatment. So in earlier case, we represented relative stereochemistry in the plane of paper, but we have to mention what is the stereochemistry of this OH and this alkyl substitution. Okay, so that is the importance of this reaction. So the stereo outcome of aldol is mainly dependent upon the stereochemistry of enolate. Okay, so in this diastereoselective aldol condensation reaction, stereo outcome is mainly dependent upon the stereochemistry of enolate, that is whether it is Z or E-enolate. Okay, so when we are move on to Zimmerman-Traxler treatment, first of all, this is the E-enolate. It can be either Z or E-enolate. Okay, so shift, attack. So you will end up with a 6-membered transition state. That is very important. Okay, so here we can see a bond formation. Here can be a bond breaking process. Here new bond formation will happen, bond breaking process. And moreover, lithium will transfer from enolate oxygen to carbonyl oxygen. Okay, ready. So this is the 6-member transition state. Finally, you can have this aldol or this aldol. What is the peculiarity of this aldol? This is called syn aldol. Why? Because this R2 and OH both are in the same side, that is both are in dash. It can be both in dash or wedge. Here it is called anti-aldol. Why? Because R2 and OH, they are in opposite direction, that's why it is called anti-aldol. So there is a two chance to have either syn aldol or anti-aldol, and their relationship is that they are diastereomers. That's why it is called a diastereoselective reaction. Now we are going to discuss deeply what will happen when we are treating with the Z-enolate. Okay, so this is our Z-enolate, that is oxygen, R2, they are in the same side, so it is Z-enolate. Okay, so shift, attack, shift. Okay, so you will end up with a 6-member transition state. So this is our cyclohexane planar structure, but the most pronounced conformation of cyclohexane is nothing but chair conformation. Now this is what is a Zimmerman-Traxler model reveals. They represented a transition state in chain conformation. Okay, So the blue portion regarded with the enolate, red portion regarded with the electrophilic carbonyl compound. Okay, that is next equivalent of carbonyl compound. Okay, so we have R1, R2, R3 from the carbonyl compound. Okay, now here R1 is pseudo axial, R2 is pseudo axial. Okay, now the most things this about this conformation or this model is that the position of R2. Okay, so the blue portion regarded with the enolate. In enolate we know that R2 and this oxygen, they are in the same set. That should be reflected in our conformation. That is, this is oxygen, it is downward, so your R2 should be in downward. That's why it is in pseudo axial. Okay, now this red portion is our electrophilic carbonyl compound. So here R3 represented in pseudo equatorial, hydrogen in pseudo axial. We can have another possibility, that is R3 in pseudo axial and hydrogen in pseudo equatorial. But this is the most favorable structure, that is R3 in pseudo equatorial. Why? Because if your R3 in pseudo axial, there will be 1,3 diaxial interaction. It is a destabilizing interaction. In order to avoid such an interaction, it is recommended to place R3 in pseudo equatorial. Okay, now we want to generate our product. What will happen? Yeah, this bond shift, so carbonyl group will regenerated, then new bond will be formed between this terminal and this terminal. This becomes OH. Okay, so like this double bond. Okay, now how can we redraw this into planar structure? Very easy. You start from R1, you should end up with R3. That is R1 in one of the terminal, R3 should be in other terminal. Okay, and beware about R2 and this OH. Okay, lithium will be protonated, it becomes OH. All others should be in the plane of paper. So R1 carbonyl compound, bond, 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 R3. Now what is the stereochemistry of R2 and OH? Very easy. Your R2 is down, that is below. Your O also, oxygen, that is OH also pointed downward. That means R2 in dash downward. This OH also in dash, that is downward. So you will end up with the syn aldol. That means this OH and R2, they are in the same side. Okay, clear. Now we move on to E-enolate. What will happen when you are dealing with the E-enolate? This is our E-enolate, that is this oxygen and R2, they are opposite. That's why it is termed as E-enolate. Okay, when we are treating with the Zimmerman-Traxler model, so this is our cyclohexane conformation. Here in earlier situation, our R2 in pseudo equatorial, pseudo axial. Now our R2 becomes pseudo equatorial. Why? We can see from the E-enolate structure. E-enolate is E-enolate. That should be reflected in this structure also. That is, it is upward. R2 in us upward. This oxygen is downward. E-enolate oxygen is downward. That's why it is E-enolate. Okay. And moreover, here also R3 should be in pseudo equatorial in order to avoid this 1,3 diaxial interaction. This is the most favorable structure. Okay, so in E-enolate, your R2 should be in pseudo equatorial upward. Okay, in Z-enolate, your R2 should be pseudo axial downward. Okay, now we can have this structure R1 double bond R2. Oh, it becomes OH. While redrawing, it is very simple. We already mentioned, you start from R1, you will end up with R2. So R1 bond double bond O, bond 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 R3. Okay, now we should be careful about R2 and OH. So here we know that R2 is upward. That means it should be in above the plane of paper, that is inwards. Clear? It is inwards. In earlier case, R2 is downward. That's why it is represented in dash. Okay, and what about OH? Here OH, it is pointing downward. In earlier case it is also pointing downward, so it should be in dash. Okay, now what is the confirmation, what is the stereochemistry? It is anti-aldol, that is R2 downward, OH is upward, OH is upward, it is anti-aldol. So the summary is that if we are dealing with the Z-enolate, Z-enolate give you syn-aldol. If you are dealing with the E-enolate, E-enolate give you anti-aldol. Okay, so here we are discussing some illustrative example. So this is our carbonyl compound. We are treating with the another equivalent of carbonyl compound. The first reagent is 9-BBN triplet. We already mentioned if you are using 9-BBN triplet, you will end up with the Z-enolate. Z-enolate give you syn-aldol. Okay, if instead of this 9-BBN I am using dicyclohexyl borane chloride, what will happen? You will end up with the E-enolate. E-enolate give you anti-aldol. Okay, so this is the illustrative example. Another, I am starting from cyclic ketone along with the LDA and another equivalent of carbonyl compound. The cyclic ketone give you E-enolate. E-enolate. So E-enolate give you anti-aldol. So here I am representing in dash. It is in words, so it is anti-aldol. Another, this is the carbonyl compound LDA, another equivalent of carbonyl compound. The thing is that here our R is bulky, that is tertiary butyl group. So if it is bulky, you will end up with Z-enolate. You will end up with Z-enolate. Okay, so Z-enolate give you syn-aldol. So here both are in wedge. This is also syn-aldol. Okay. Another problem here, the R group is not so much bulky, so that give you E-enolate. E-enolate. So E-enolate give you anti-aldol. This is in wedge, this is in dash. Okay, clear. Thank you. Take care.